Welcome everyone. Today in this video we will use linear approximation to prove the following equation. The following approximation actually. So if we have 1 plus epsilon, oops, that's not a nice looking epsilon there, 1 plus epsilon, and we raise it to the power of alpha, then this is approximately equal to 1 plus alpha times epsilon, as where epsilon approaches 0. And in math, epsilon is often used as a number to refer to very, very small numbers, like infinitesimally small, very small numbers. So near 0 it means. And alpha here is just a number. It could be 3 divided by 2, it could be 5, it could be negative 17. It is just a number, and I don't know why they choose to represent it with alpha, but that's how we are going to do it. So how can we use linear approximation to prove this following statement? Well, first let's remember what linear approximation was. The formula for it is as this. F of x is approximately equal to the derivative at the point x naught times x minus x naught plus f of x naught. I proved this approximation in the last video. So if you don't know how this is correct, go check that video out. And so when we look at this formula, we see that first we need to define a function f, and then we need to choose a starting point x naught. And in our case, we will choose x naught as 0 because we are interested in the case where epsilon is approaching 0, right? So we will choose x naught as 0. And for f of x, we will just make it like this. Let me write it. We will define f of x as 1 plus x raised to the power of alpha. Let me write it nice, like this. Okay, so this is the setup, and now we are ready to do our proof. Actually, before doing the proof, also let's take the derivative of f of x. We will need it. So its derivative will be using the chain rule and the power rule. We will first take the derivative of 1 plus x raised to the power of alpha with respect to x, with respect to 1 plus x, and then we will take the derivative of 1 plus x with respect to x. So the first derivative will give us alpha 1 plus x raised to the power of alpha minus 1, right? I am just using the power rule, and the second derivative will be just 1. So we don't even need to write it. This is the derivative. Great, so let's start. Let's open a new page and start our proof there. So for f of x, we are interested in finding f of epsilon. And don't forget, epsilon isn't just a number. It is a number that is very, very close to 0. And this is approximately equal to the derivative of f at point x naught. Well, we said that x naught is equal to 0, and we have a formula for the derivative of x, for the derivative of f. I don't know why I can't pronounce those, but anyway, for the derivative of f at point 0, we will just substitute 0 for x. So we will have alpha 1 plus 0 raised to the power of alpha minus 1, right? This is how we do it. And so you look at this, the inside will give you 1, so you have alpha times 1 raised to the power of alpha minus 1. 1 to any power is 1, so we have alpha times 1, and 1 times any number will give you the number itself, so we have alpha. That's what I am writing here, because don't forget that we first had the derivative at point x naught, and our x naught is 0 because we are interested in our function's behavior as epsilon approaches 0. Now we have x minus x naught, so our x is epsilon, and oops, that was a parenthesis, and our x naught is, as I just said, 0. then we have a plus, and we have the value of our function at point x naught. So if we, let me do it here with red. If we plug in x naught, which is 0, to our formula, we have 1 plus 0 raised to the power of alpha. So it is 1 raised to the power of alpha, which is equal to 1. Which means we can just put a plus 1 here. So let's simplify this, and we are actually very close to the end. And actually, let me do it in a below line. Okay, we have approximately equal sign alpha times epsilon plus 1. And f of epsilon, well, look at the definition of f. It is 1 plus x raised to the power of alpha. So we substitute for x, and we have 1 plus epsilon raised to the power of alpha. If we make this a little nicer, make it a little more familiar, we see that we have, I meant to put an approximately equals there, 1 plus epsilon alpha, or you could say alpha epsilon, which is the correct as epsilon approaches 0. So this was the focus of this video, and we have actually proven this. You might be wondering how accurate this is. So to test that, we can do a percent error check, just like we did in the last video. And for that, I am going to grab a calculator, and I will be back in a minute. All right, I am back. It seemed like less than a minute to you, and it actually was less than a minute. So let's say that for epsilon, we choose 0.1, which is very close to 0, to be honest. And for alpha, we maybe choose, I don't know, let's choose 4. So our approximation says 1 plus 0.4 raised to the power of 4, 0.1 raised to the power of 4 is approximately equal to 1 plus 4 times 0.1. So we are claiming that this is approximately equal to 1.4. And as you can see, this formula can come really handy, because it was very easy to compute that it will be approximately equal to 1.4. And let's check the actual value. And it turns out this is actually equal to 1.4641. So as you can see, it is very close. You can check the percent error if you want. Percent error, you would have them subtracted from one another, and then you divide by the actual result. So let's see what this gives us. And this gives you, a percent error of 4.378%. As you can see, this is much higher than the one we had in the last video, but it is still a good approximation if you need to do it very quickly. And this formula that we started with, it isn't just used for, computing like what is the 4th power of 1.1. This is actually used for very, very important stuff. For example, you could use this while calculating the force that acts on a dipole in an electric field. You could even use it for that, because in atomic scale, the distances become very, very small. So any distance is actually an epsilon. It is very close to 0. So this approximation is very, very important in science. It is used a lot, and in this video I proved it. I hope you found this video helpful. If you have any questions or comments, please write them in the comment section. I hope to see you in another video. Until then, take care.